Good morning, students. Today's topic of discussion is deduction in extended semantic networks. Let's quickly recapitulate the topic that we covered earlier to form the context for this. We learned that knowledge is represented in several forms. Like we represent A in two forms, capital A, small a. Likewise, you have a knowledge. Let us say, if it is said that the sky is cloudy and it may rain today, this can be represented in the form of logic, predicate logic, or in the form of semantic networks. We discussed earlier that logic is quite limited, and you have to use the variables, predicates, functions in order to represent the knowledge. Whereas, in order to understand and essentially represent a larger and more bigger paragraph sort of knowledge, the method that was employed was semantic networks. Semantic network was in the form of a tree, and we had concepts and their relations or links that we could represent in the form of a semantic network. But later, it was observed that there were some limitations in semantic network. Therefore, extended semantic networks were, um, you know, discussed. Extended semantic network has got several additions besides having all the features of semantic networks. For instance, look at this. This is extended semantic net representation, and this is also an ES net stands for extended semantic net representation. So these are all the notations and the symbols used in the extended semantic network. In this topic, deduction in extended semantic network, the topic of inference is explored further. How to infer? What do you mean by infer? For example, if there is a statement given, the statement is John is having uh, headache today in the morning. If John's mother says this to John's father, John has headache. What does father infer? What does father infer? Consider John is a school going student and he complains about his headache in the morning. And then when mother says this to the father, consider that father while going to office drops John to the school. Father understand that probably John is not going to school today. Why is not John going to school today? Because he has a headache. How this father inferred that he's not going to school today? Mother said John has headache, but father has inferred another statement, which is a sort of conclusion from the previous statement, uh, which means he is not going to school. Generally, when students have any health problem, headache, stomachache, or any other thing, then their parents allow them not to go to school on that particular day because he has headache. They he understood Father understood that he's not going to school because of his headache. How are we going to infer new statements, conclusions from the existing knowledge base in extended semantic network is the topic of discussion now. There are two types of inference mechanisms. What are the types of inference mechanism? If you consider this John example again, when mother says John has headache, consider there are two statements. Uh, John is John has not uh, waken up because he has headache. John has a headache, so he has not waken up. From these two existing statements, when some other a new statement is derived, this is forward reasoning inference. Forward reasoning means you have got the knowledge base, there are assertions, true statements. From this, you derive a new statement. What does forward reference means? From the existing base, you are going to uh, derive new, which implies apparently that it is moving in forward direction from what is available to what can be derived. Backward chaining, backward reference inference mechanism, backward reasoning inference mechanism. When it is backward reasoning inference mechanism, there is a statement given. This statement has to be uh, either accepted or rejected based on the knowledge base. In other words, this new statement, what is being given, is validated with the existing knowledge base in order to um, state whether it is true or false. That is backward reasoning inference mechanism. Forward reasoning is also called as bottom up approach. We start with given assertions. Given assertions means what? All the statements that are there in the knowledge base. Those are known as assertions. And derive new assertion using the clausal rule. And backward reasoning inference means it is top down approach. Top down approach is having a uh, query which has to be proved from the set of clauses using resolution repetition method in causal logic. This all we all actually learned. In causal logic, we saw how resolution repetition method is used to determine whether the clause, given clause is true or false. These inference rules, forward reasoning inference mechanism and backward reasoning inference mechanism, uh, also known as bottom-up approach and top-down respectively, are also available in extended semantic net. Forward reasoning inference. Let us look at an example. Consider an ES net is given. Deductions or resolutions could be applied using modus ponens rule of logic. We learned modus ponens rules in the last chapter, where we say if is implied by B and B, if both are true, we can conclude that A is true. Consider the clauses is a x comma human implied by is a x comma man. This is x is a man implies x is a human. When you replace x with John, x is equals to John. Consider x is human as A, and what is B? X is man. X is man. Okay. When we say X is man, and in place of X we are putting John, uh, what does we conclude that John is a man, which in turn implies that John is a human. Using modus ponens rule, we can derive that John is a human holds true. How John is a human holds true? Because John is a man. And it is said in the logic rule that if X is a man, he is a human. This statement is true. It is an assertion. Because it is true, we can conclude that John is a human. This holds true. How can this be done using ESNet representation? This one, the set of clauses is represented in the form of a ESNet. John is a man. Actually, uh, John is a man. This rectangular box is like B. X is a man. X is a human. This is a contradiction statement which says that X is both. If X is a man, X is a human. How do you represent contradiction? We learned that when there is a contradiction, we write in this manner: one dotted line, another one solid line. X is a human. X is a man. This is the contradiction. And then we say that John is a John is a man. When we say John is a man, we know that if X is a man, X is also a human. When John is a man, John is also human. This is inference or deduction. What are we deducing? That John is a human. Alright, this is a forward reasoning inference mechanism using ESNet. Backward reasoning inference mechanism. In this, conclusion is given. What is the conclusion? John is a human. Whether it is right or not, that is proved through this ESNet. How it is proved? Through resolution refutation. What do you mean by resolution refutation? It means that the query is proved through contradiction. All right. We can prove conclusion or goal by adding denial of the conclusion. Denial of the conclusion implies that we are making it false in the beginning. And later, if we could derive um, the conclusion from the set of clauses, we say that we have proved it by contradiction. And how do you carry out this task? By performing successive steps of resolution until an explicit contradiction is generated. Contradiction has to be generated. When contradiction is generated, uh, um, it is said that query is proved. What is to be proved? We have to prove that John is a human. How to prove that? Here, what are the given set of clauses? X is a human implied by X is a man. Also, it is said that John is a man. All right. If it is A implied by B and B, both are true, then A is also true. What is A? A is X is human. What is B? X is a man. And in place of X, you are substituting John. And we are saying that John is a man. To prove that John is a human, this is John is a human. This is a contradiction line. When it is a dashed line, it is a contradiction line. Means you are adding a contradiction here. To this contradiction, how to prove? We could prove that a human means this clause already available in the knowledge base that you are adding here. X is a human, X is a man. And from this second clause, we know that John is a man. Because John is a man, look at here, John got this is a human as a contradiction like X. X is a human, X is a man. Here you find that it is a dashed line. Observe that there is a solid line in between X and is a. When you apply a dashed line between John and human, we know that John is a man is a true statement from the set of clauses. Therefore, John is a man is this solid line, and already it is given in the figure earlier in this network that John is a human. And apparently, here it is proved that John is a human. Contradiction or empty network. This is how it is generated and proved. When you substitute X is equals to John, John is a human, John is a human. When you substitute X is equals to John, you say that here. Here in place of X you put John, you get John is a human, John is a man. Contradiction or empty network. which is known as a contradiction or empty network. And therefore, it can be concluded that inferencing and inheritance are important and embedded capabilities of ESNet. Example for illustrating inference methods. Consider the following example represented in clausal form. This is a clausal form. X is a living thing implied by X is a animate. If X is animate implies that X is a human. If X is a human is implied by is a man. Remember, these set of clauses are not the exhaustive list of a real world knowledge or information. It is something that is a subset. Here, the subset says that John is a man, X is a man implies X is human, which implies X is animate, which implies X is a living thing. All right, and here this figure number 7.10, that is ESNet representation, extended semantic net representation. We see here X is a living thing, is a animate. How we got this? We know that living thing X, no, this one should be easy. Is a living thing implied by is a, what is there? Is X comma, let us see. First it is a living thing, animate. Animate in human. X is a living thing implied by X is animate. X is animate is implied by X is a human. X is a human implied by X man. X is a man. Alright, students. Then X is a not X. Now you are substituting John in place of X, and we are saying no, no, we are not substituting. It's just a statement. John is a man. Now let us see how this clausal representation is converted into a ESNet representation. This one is X. X is a living thing. X is animate. This is one clause. Second clause is X is animate. No, here we are using different names. X1 is animate and X1 is a human. And in place of, look at here, in the first clause we have X, that is retained as it is. In the second clause, in place of X we are using X1, X1, X1. And in place of third clause X, X2 is. It is renamed for the purpose of ESNet. X2 is a man, X2 is a human. This is another clause. So three clauses. And finally, we have the last statement. It says, John is a man. All right. Is this clear? This is ESNet representation from this clauses or set of clauses or clausal notation or clausal representation. This one is ESNet representation. Using forward reasoning inference, uh, the new assertion, which is John is human, can be inferred or derived. How can you derive that John is human? The steps for inferring that John is animate, John is a living thing, okay, both could be inferred similarly. Okay, here we what do we say? We say that right here John is a man. Look at here, x2 has got a value John now. When x2 is equals to John, in place of x2 when you are putting John, you are concluding that John is a human. John is a man, John is a human. When x1 is initialized with the value of John, what does it says? This x1, okay, look at here. Here we have removed x2. In place of x2, we have added John. John is human. Uh, this at this place, because this one is true, this one is like B, this is A. Because this one is a true statement, John is a man, and you are substituting x2 to John with John, you have removed this part. This part is removed. You have got only this part. John is a human. Here, John is a human. When you assign John to x1, what happens? Here, John comes here. You see here, John here in place of x1, it is John. From here, we start reading John is a animate. John is a animate. And once again, when John is animate, once again, when you place John in X, we can conclude that John is a living thing. Before that, if you are ending it here, you can conclude that John is animate. Is John is a animate. This can be inferred. Actually, there are many things that could be inferred from this ESNet. What are those things that could be inferred? We could infer John is a man is already given. John is human. We can infer John is animate, and finally John is living thing. All three can be inferred from this ESNet by assigning John to different variables. These variables which are x, x1, x2. Here what is proved? We have stopped our derivation here and by stating that John is animate. Animate, you know animate, right? The one who moves from um, one place to another place, which has got animation kind of thing. Animation means movement. Further, John is a living thing can be derived by binding X with John. When you assign X to John, you can infer that John is living. Backward reasoning inference. That was forward reasoning inference. In forward reasoning inference, we could derive John is a human, John is animate, John is a living thing. We can derive three conclusions. In backward reasoning inference mechanism, look at here what happens. John is a living thing. This is a query. If, to prove whether this query is true, using backward inferencing mechanism, what do we have to do? The first step is add a denial of the fact that John is not a living thing. We prove by contradiction. We prove by contradiction. Proof by contradiction is equal to saying that John is not a living thing. And how do you add that? By using this dashed line. Mm, Here, John is a living thing. This a new clause is added, which is a query that has to be proved from these clauses, whether it is right or not. How is it done? John is a living thing. We know that John is a man. When we bind John to x2, we get like in this manner John is a human. Further, when it is binded to x1, in place of xy, if you put John here, here uh, when x1 is when John when we bind John to x1, we get John animate, and when it is bounded with is a, we get John is a living thing. We prove that this given statement is true with respect to the clauses available. Whatever I explained is shown here. This part is removed. This part is removed, and John is directly connected to human. Look at here. John is directly connected to human. That part is removed. Further, when assignment of x1 with John takes place, this part is removed. This part is removed, and John is linked to animate. In the next figure, we will look how it is done. Look at here. If this part has been eliminated, which part is eliminated? From this is a this part is eliminated. Or in other words, we can also say that this John is animate. When you are binding John to X, this part is also removed. Now John is directly linked to living thing. When you remove this part, John will go here. All right. Next. Hmm. This part is not John's. Finally, the query is solved. How it is solved? It is leading to an empty clause or contradiction. If it leads to empty clause or contradiction, means this John variable is linked to another variable living thing using two links. One is the dashed line link, another one is the solid line link. This dashed line link and solid line link, when you combine together, it is called as an empty clause or a contradiction. Because we achieved the contradiction, we can say that it is proved that John is a living thing is true, and this query is proved. Mm, Another example, these are the sentences. Okay, try to understand these sentences. Anyone who gives something he likes to a person likes that person also. Hmm? John gives an apple to Mike. John likes an apple. Hmm. What happens here? You see, what this sentence says is, if somebody, say X, is giving something, say Y, to another person, say Z, and whatever he is giving, here in this case it is Y, whatever he is giving, uh, he likes it. Okay? He likes whatever he is giving. What does it implies? And he is giving uh, that Y to Z. This first statement say that if anyone gives anything that he likes to anybody, it means that he likes that person as well. And it is said that John gives an apple to Mike. John is giving an apple. Here we are binding variables with values. What are the values for X? For X, we can say that it is John. For Y, it is Apple. For Z, it is this Mike. In clausal form, the same sentence is written as action E, okay, is give. Object E is Y. Action E, no, the actor. The actor performing the action E is X. The recipient, the one who is receiving the action, means the object through the action, uh, is essentially here the Z. Means the recipient of action E is Z. And it and also we say that X likes Y. What is X? Yes, X is John. John likes here. X, John likes apple. This is the first statement. This is first sentence. And here we are just expanding it. We are saying that E is a action which is give. E is um, an object which is apple. He is actor, which is John. He is recipient of the action, which is Mike. And also we say that John likes apple. What do you understand here? These are the clauses, set of clauses, and this whole set is known as clausal representation. How you obtain this clausal representation? By understanding and representing English sentences given here within double quotes. All right. E is a variable which will be bound to actual event. Capital E is a variable which will be bound to the actual event. Bound means what? You can say x is equals to John. Here, small e is the process of resolution. This is small e. From 1, this is 1, 2, 3, 4, 5, 6. From 2 to 6, these 5 statements denote the process of resolution. This is ESNet representation. These 6 clauses are represented in ESNet in this form. What is the form? This capital E, action is give, capital E, object is Y, capital E, actor is X, capital E, recipient is Z. And this should be read in reverse direction. Did you understand this? This also. Okay. Now forward reasoning inference. In forward reasoning inference, we are binding apple to Y and John to X. Here, this one and this one. When we bind the network shows first. Okay, there is another rule which is known as unification, unifying, merging. When you are unifying, E and small e and capital E, and you are binding Z with this Z with Mike, Z with Mike, and this E and E are unified. Unified means merged. When you merge that, what do you obtain? You obtain only this part, which is John likes Mike. Through forward referencing, uh, no, forward reasoning inference mechanism or forward inferencing, it is inferred that John likes Mike. There is a link likes between John and Mike, and which is deduced after eliminating all the links. After you are unifying and eliminating all the links, assertions and denials. Assertions are these lines, denials are these lines. All are eliminated except this, and it is proved that uh, John likes Mike. Uh, it's not proved, and in fact, it is derived or deduced or inferred. These are synonyms. Backward reasoning inference is here we have to prove John likes Mike. This query is given, and we start with this query. How do we start with this query? By using the denial line, the contradiction, this dashed line here. John likes Mike. Actually, here you see all bindings happening and add addition of denial link. When denial link is added and these assignments takes place, you look at here. Here we know that John likes apple. Here we are binding apple, binding Y to apple, and then here Y is an apple. When we do that, and for E equal to E, we get an empty network. You see here, capital E, small e. Capital E action give, here also action give. This one. Apple is object object. This one. John is actor actor. Mike is recipient recipient. We get an empty network. Because we get an empty network, it is proved that the query given is a valid query which has been deduced, which can be inferred or deduced from the uh, network, this network, the extended semantic network. All right, I hope that this is clear. Okay, if any doubt, please ask. Moving ahead to inheritance. In conventional semantic network, conventional. Conventional means just the semantic network, not the extended semantic network. Lower level node in is a hierarchy inherit properties from higher level nodes. Look at here. Unless the properties are redefined. Hmm. If consider that there are properties. Hmm. Here, here the property is assigned, attached. This property. What is the property? Two legs. This property two legs is associated to human. This is a node. This node is a higher level node compared to this man. This is a lower level node. This is like a superclass. This is like subclass in inheritance. higher level node, lower level node. This lower level node inherits the property from higher level node. What is the property? Two legs. If we say humans have two legs, by default it is applied to man as well, because man is derived from human. All right. Yeah. Hmm. And in order to show that John has two legs, when we say man is a human and has two legs, later there is another clause stating that John is a human, we can infer that John also has two legs. How can we infer? Because John is a man and man is a human and human has two legs. To do so, there is a denial link. Denial link with this dashed line is added between John and two legs in the network. Look at here. This denial link, John and two legs. This line. When you bind x2 to John, what happens? There is no x2 now. It is just John. And here we achieved contradiction. How we achieved contradiction? Uh, John is a human, and John has uh, or part of John is two legs, part of human is two legs. Look at here. This through this we arrived at contradiction. Because we have arrived at contradiction, it can be proved that John has two legs. Is this clear? John is a human who has two legs. Is an assertion, means a true statement. John has two legs is a denial, and we get contradiction. Because of this, we get contradiction. Because we got contradiction, we proved that by contradiction that John has two legs. Any doubts, students? How do we implement? Moving on from the theoretical concepts to the implementation. How can we implement ESNet? This could be done by using a programming language or any tool which facilitates the implementation of the semantic networks. And here, the difference between conventional semantic network and extended semantic network is that procedures are generally written in the host programming language, whereas in ESNet, procedures are integrated with the database and executed by the same general purpose mechanism. This is the difference with respect to the implementation. When you implement ESNet and semantic network, when there are procedures, right? Procedures for the forward inferencing, backward inferencing. Uh, that procedure is written in the programming language in conventional semantic network, and in extended semantic network, it is a part of the database or the knowledge base. And uh, the example is John gives an apple to Mike, and if we ask who takes an apple, then the knowledge representation scheme should have some mechanism of storing the knowledge. That every act of giving, there is a corresponding act of taking. Knowledge base is created. Like when you develop a database, You create tables. When you develop an AI system, you develop knowledge base. In the knowledge base, all these sentences are coded in the form of uh, in the form of in any programming language. This could be done. Nowadays we use Python programming language to do all this. And also this whatever we are learning, these are all traditional methods. The modern methods and the current state of the art is machine learning. We have got latest technologies, uh, uh, deep learning, convolutional neural networks, and then random forest and all that. But these are